Well, at least you can see my screen. So I will be the chairperson of this session. My name is Juana David. I work at Technalia. And today in this session, we will have 6 presentations. We are supposed to finish about 11:45. So each presentation will be about 15 minutes long with 5 minutes for questions. And please write down the questions on the chat window as usual. And at the end, I can read them out for you. So I would like to introduce the first speaker, which is Anastasia Sliovsareko from DMT. I invite you, Anastasia, to present.
Thank you, Anna. Just a moment to share my screen. Is it visible for you?
Yes, it is. Well, it was. No, it is again.
Okay, great. Yes, first of all, good morning all. Kalimera. Very nice to be here in this very nicely organized virtual workshop. I'm Anastasia Sliusarenko, R&D process engineer at DMT Environmental Technology. And the pitch for today would be about the different, the current practice and developments for CO2 removal from 3 different gas streams, post-combustion flue gases, natural gas, and biogas. Starting off, just a brief introduction of who we are and what we're doing. DMT is an engineering company with over 30 years of experience in gas desulfurization and biogas upgrading. One of our main product lines, the Carborex MS, is utilizing membrane technology to separate CO2 from biogas, so producing pure biomethane. Of course, DMT is not limited only in these fields, as our department is working on various projects in the general frame of environmental processes and sustainability. DMT is a Dutch company located in the northern part of the Netherlands. However, we have offices all around Europe, US, and Asia. And to conclude, DMT is a global team, and as we like to say, our goal is to create a clear and prosperous future. Before I get started, I would like to say that the results of this presentation are the fruits from the research conducted mainly by TMT and TU Eindhoven in the framework of the Biocommon project. You may already have heard from Anna and Marcin today and yesterday about this. One of the main goals of the Biocommon project is to fabricate bio-PIBA membranes and to test them in a relevant industrial environment. So one of the roles of DMT as a biogas expert is to provide the demonstration location and the test kit for the pilot testings of the modules. So without further ado, let's get started with the first stream, which is the post-combustion flue gases. So even though there is an environmental need to try mitigating anthropogenic emissions, we see that at the moment there is insufficient economical incentive within the industrial parties to implement such practices. Some of the reasons behind this are that carbon capture and storage techniques are reported to be generally costly and contribute to around 70 to 80% of the total cost of a full CCS system, including capture, transport, and storage. Furthermore, we see that many direct air capture technologies are still at low TRL, which creates an uncertainty for cost estimation. However, that does not mean that we're not expecting to see large-scale installations in the next period, at least in Europe. And final reason, and I believe the most important one, is that at the moment, EU allowances are very low, lower than the prices for CO2 capture. Well, despite the limited implementation, there are several techniques to separate CO2 from flue gases. For example, chemical amine absorption. On the right, you can see, I don't know if my cursor works well. You can see the first commercial plan implemented in Texas, US. Regarding membrane separation, to our knowledge, this has not reached full scale for this application yet, rather only pilot scale. Other technologies may include PTSA or calcium looping. Flue gases are not the easy stream for membrane separation. Well, let's take as an example the flue gas released from a power generator. This is released at relatively low pressures and with low concentration of CO2 between 4 and 20%, coupled with huge gas flows. This already indicates that permeants play a huge role here. And yeah, in order to reduce both the cost of the material and the energy consumption for the capture. In order to be competitive with amines or reach a target of 90% CO2 removal for installed prices larger than 50 euros per square meter, it is reported that the permeant should be higher than 2000 already GPU and selectivity above 30. Other requirements for such systems include chemical and mechanical compatibility, stability, reasonable lifetime, easy fabrication and packaging, freedom from fouling, could also be resistance to high pressures. So far, we see that advanced membranes are required for this type of application, such as high-performance polymeric-based materials, could be polymers with intrinsic microporosity, polyethylene oxide, thermal rearrangement, or polyimide-based membranes. Finally, polyvinylamide-based fixed-site carrier membranes tested in pilot scale showed good results under humidified conditions. Okay, so here we see, a two-stage system. I have to say that generally membranes are good for bulk separation. However, when the concentration is low, the membrane has difficulty to satisfy both the high purity permeate and the low concentrated retin-day. Therefore, one stage is not expected to be sufficient, even with high pressures and high membrane areas. On the right, you can see a generic multi-stage system. The downstream is used to minimize the target, the downstream is used to enrich the permeate, while the upstream to minimize the targeted components. For example, when the objective is high purity permeate, the strategy will be to enrich, and therefore 2 or even 3 stages may be selected. Okay, go for the natural gas. Natural gas before entering the pipeline requires treatment in order to reach the specifications. Currently, the most applied technology for natural gas sweetening with focus on CO2 removal is amine absorption. However, amines can be relatively costly and also have high footprint. However, we see that membrane application is increasing. While in 2008 only held 5% of the market share, we're estimating that by today this would be between 5 and 10% already, as membrane technology started to be competitive. Commercially, polymers are dominant in the market, and specifically cellulose acetate, polyamides, polyimides, and perfluoropolymers. Also, silicon composites and hybrid amine membranes are provided. On the right, you can see, let's say, a competition map of membrane technology with amines. I think it is clear that our amines are favored for high gas flows and low CO2 concentrations, while membranes will require lower flows and higher CO2 concentration. Regarding the different configuration used, the first important step is to pre-treat the stream to remove aromatics, heavy hydrocarbons, oil mist, and particulates. Of course, this is to prevent fouling for liquefaction of this type of components and to prevent plasticization. For natural gas, 1 stage, 2 stage, and even 3 stage is applied. Okay, so 1 stage systems are quite simple. They're low cost and with low maintenance, and are preferred for small gas flow. We see here also that the methane loss is quite high and ranges between 10 to 15%. Of course, you can imagine that for higher streams, 1 stage would not be sufficient. because we will have a huge product loss. Here, two-stage will be preferred, and a three-stage system is preferred for offshore applications. As you can see here, the third system is not really comparable to the first two, as we have higher flow, 5-fold, and also one can observe that the concentration of the product gas here is relatively high, but this would not be a problem, as usually this is polished onshore. For the industrial requirements, what we need to consider is the initial concentration of the flow and the grid specs. Let's agree that inflow consists of around 8% CO2, 80% methane. It's also characterized by very large flows and low pressures. Also here we have 3 different gas qualities. High, low, and Groningen quality here in the Netherlands. The qualities differ for Wobbe index, which is the interchangeability of the gases and the amount of nitrogen. Furthermore, one also should think about the network that the natural gas is going to be injected in, as the pressures vary. Okay, so we see here that for H gas, from 80%, we need to achieve more than 90% methane purity. So as an example, for the H gas, then membrane should achieve around 80% removal efficiency. Here, permeance and module size play key role, at least onshore. And yeah, for this research, it was quite challenging to determine the permeance and the selectivity required. However, in the framework of the Biocommon project, the target set was above 100 GPU permeance and selectivity around 50. Commercially, asymmetric hollow fibers and modules between 4 to 12 inches diameter are provided. Regarding current material studies for natural gas applications, we see that polymeric, fixed site carrier, composites, and carbomolecular sieves are trending at the moment. And finally, for the biogas upgrading, many technologies are currently applied. Most applied is water scrubbing. Second comes membrane separation, then chemical scrubbing and PSA. Yes, for biogas, membranes hold a large share in the market in comparison with natural gas, and at the moment, the dominant commercial membranes are polymers. Okay, the membrane system configuration, in order to achieve the desired output, should consider 5 to 6 factors. These include the methane recovery, the energy demand, the membrane area required, the cost, the desired outlet pressure, and pretreatment if applied. For two-stage system, the methane slip is typically around 2 to 4%, and for three-stage, half to 1%, depending on the suppliers. Yeah, one stage is not typically preferred in this type of application. The methane slip is an important parameter as it indicates the product loss, and one should be aware that there is a trade-off between methane slip and CAPEX OPEX. DMTs currently implement three-stage systems in the European market. For the industrial requirements, we have an initial flow of around 45% CO2, 55% methane, which typically includes various contaminants such as H2S, volatiles, ammonia, and water, which can degrade the membrane significantly. Biogas also comes in relatively low flow rates and is treated in relatively low pressures between 4 to 16 bars. Overall, we can conclude that selectivity plays a significant role in this application. In the case that the biomethane is inserted to an H-gas grid, as a previous example, here 90% removal is required, with methane slip lower than 0.5%, as you can see in the table. And why is with removal 4? Of course, to increase the calorific value. That means that the requirements of the membrane specs translate to a permeance of 50 to 100 GPU and selectivity around 50. Commercially, hollow fiber and spiral wound membranes are provided with the modules between 4 to 8 inches. Regarding the state-of-the-art materials, we again see that composites, fixed site carriers, metal organic frameworks are trending, and especially for fiber-based membranes, graphene, inorganic and nanocomposites. Many studies are also conducted. And I think I conclude with this. I thank you very much for your attention. I will be happy to hear if you would have any questions, and I'm looking forward for the rest of the presentations.
Thank you very, very much for the presentation. So far, I don't see any question in the chat window. Please address your questions there. In the meantime, I would like to ask one question myself. So you say that membrane separation is competitive with ammonia separation in the case of higher concentration and lower gas flow rate. If I understood correctly, it's like this. Then my question is for post-combustion carbon dioxide separation, where we have high gas flows and low concentration, what would be the membrane cost necessary in order to make membrane competitive with ammonia separation, if you know that?
Thank you, Anna, for your question. Yes, indeed, they are competing with amine. So they're using chemicals to polish it. Unfortunately, I don't have this number on the top of my head, but I would be happy to catch you up on that later on.
Okay, I think because it's something we have to address because I guess the price for the membrane should be lower than the current state price of the membranes, because it's exactly where it's more competing with amine.
Yes, and also, what I can say, however, is that in electrical demand for the consumption. So I can talk about the OPEX. Amines are similar with membranes. However, amines also has very high heating demand. In order to increase the temperature around 120 Celsius, if I'm not mistaken. But it's something we can definitely look into more.
Okay, we have 2 questions from Leonardo Rosses. One is, what is the durability of the membranes?
Could that be specified in a sense that lifetime? Does that translate to lifetime?
I think so. It might be.
I can unmute. No, my question was probably there's some periodic replacement of the membrane due to the decayed, say, performance. That's what I meant with durability. So if you take into account the cost of replacement, how large do you think this maintenance cost is compared to the initial capex?
Yes, so indeed, there is a degradation. I can say that you can change the membranes though in a lifetime of 5 to 10 years. So I don't think it's really that much of a comparable, if I can say that.
Okay.
Did that answer your question?
Yeah, quite. It's quite long. Durability. Yeah, thanks.
Thank you for your question.
So this is also replying to the other question, no? taking into account periodic replacement of the membranes, what is the impact of such maintenance cost versus the initial capex?
Yeah,
Okay.
unfortunately.
No, you answered. Yeah. I mean, that you can even say the capex of the membranes once every 5 years. Yes. Thank you.
Okay, then thank you very much. So if you have further questions, please address them via email. And now I will go to the next presenter. I will, I'm trying to share again. So it's Dr. Kim. Please start your presentation.
Thank you. I will share my screen then and hope it works. Do you see my screen now?
Yes.
Oops, this was, like this. I'm Ina Kim. I'm a research scientist at SINTEF. We're coordinating Realize project. So it was shortly introduced this morning, but I will go now through the more details. This presentation is prepared together with my colleague at TNO, Juliana Monteiro. No, it doesn't move to next. So like this. Our project is relatively young. We started 1st of May 2020, and the duration of the project is 3 years. We have 14 partners in Europe, 2 partners in China, and 1 refinery partner in South Korea. Project budget is 7 million euro, and it doesn't go. And we have our partners involved in different work packages to work together. On the development of it's on optimization of the solvent-based technologies for refineries. Then these technologies are solvent technology for CO2 capture and also solvent management technologies to reduce solvent degradation and emissions from the plant. Then we will demonstrate those technologies in pilot scale on-site refinery and also off-site. It's a larger pilot scale at SINTEF. And demonstration data, results from this demonstration campaign will be used for techno-economic assessment of integrating the full-scale capture plant at refineries. Refineries are different. They are really different from each other. So to have several business cases is important for the project, and we will explain it. We collaborate with mission innovation countries. It was a requirement in the call, but it's also interesting to see how other countries work on CCS. We have a work package on societal impact assessment, on risk barriers and business models with partners in UCC and Scottish CCS Centre working on it together with NTNU. And we have also advisory board in the project, including TCM, Petroineos, Saras, Concave, Global CCS Institute, and Science Foundation Ireland. So we have some meetings with them to discuss where the directions for the project and what we can do. So the objectives. Our objective is to reduce the cost of capture. To reduce the cost of capture, there are several contributions to that. First, the solvent energy requirement in the solvent mentioned just in the previous presentation. There is thermal energy needed to recover the solvent and to circulate it again. So with our new solvent, compared to the baseline solvent, which is 38% MEA, we can reduce energy demand by 30%. But that's not all. By reducing degradation of the solvent using solvent management technologies, and that's what we will demonstrate in our project, we can reduce losses of the main solvent component by more than 80%, again, compared to reference solvents, which is 38% MEA, widely used now in small and moderate large scales. Again, use of plastic as a part of the as a substitute for some parts of the facilities, for pipelines, or for packing in the columns, for example, can also lower capital cost. And our projection is that it up to 15% can be reduced if plastic or composite materials cheaper than steel can be used in the capture plants and facilities around it. Then integration is also very important. You maybe know that the recent report from Gasnova on techno-economic assessment of full-scale plant CCS project in Norway, they came up that capture plant contributes to with 25% to the total cost for CO2 capture, while integration of capture plant in the hosting facilities contributes with 30% of the total cost, and the rest is facilities for transport and storage there. So it's very important to see where it is possible to save cost on integrating. And we will produce a CO2 simulation tool which will be free access to those industries who are interested in it to test. So to try different CO2 capture scenarios for different refineries. We did some projection of cost reduction for retrofitting CO2 capture using all these possibilities in cost reduction, and compared it with the results from the earlier EU project recap, where desktop study was done for this, and with the reference solvent 38% MEA, and we can see that total cost reduction can be achieved at least by 30% compared to that case that was simulated in recap using our solvent and innovations developed in Realize project. So this is a cost reduction, and it's done for a specific refinery. It will be different from refinery to refinery. So what we will demonstrate in Realize and how we will demonstrate, it's a bit difficult with refineries. Operating refineries is explosion-proof zone, so we cannot just go with any pilot and install it on-site refinery. And we come up with a solution that we think is really feasible and can help to do this demonstration economically. So we first optimize our solvent and solvent management technologies in lab scale with simulated environment, and then we bring a mini pilot and connect it to the sampling lines of the operating refineries. This mini pilot have to be done ATIX proof, of course. And then we sample and we test our solvent inside this mini plant for long term. We plan to test at least 8 months at refinery and sample gas from different stacks, so that we will combine impurities from different stacks and see what will be the effect on solvent. Then this solvent from this mini plant, it's about 20 liters solvent inventory in it, containing all those impurities and partly degraded, probably. Also, we hope it will be minimum degradation. Still, there will be some. We will bring that solvent to a larger pilot plant, which is full height pilot plant at Sintev we have, and we can use simulated flue gas and run this solvent mixed with the fresh solvent. This full height pilot plant requires about 600 liters. But if we mix it with 20 liters of the degraded solvent, it will resemble a partly reclaimed solvent, which is normal procedure in solvent technologies. So there will be 2 campaigns focusing on different things. The first campaign with mini plant will focus on solvent degradation and see what emissions also will come depending on different flue gas impurities. However, energetic numbers will be not straightforward to use from that demonstrator because it's much smaller and its residence times is smaller. So that's why we will use a larger pilot plant, and where we will measure energy consumption, real energy consumption that will be for this mine system. In addition, our full height pilot plant will be connected with a CO2 liquefaction unit. So we will liquefy the CO2 that is produced in this facility. And liquefaction unit has several compression stages. We will take samples from each stage and see what happened to the quality of CO2, because as we were told by some industries, normally what you have in flue gas, you will find in CO2 too. And knowing that requirements to CO2 may be very strict, we really want to know what to do. And also doing this analysis and analyzing CO2 quality, we think we can adjust the capture process some in different ways so that CO2 quality can be also partly improved. So what are innovations we plan to test in REALIZE? It says I mentioned novel low energy solvent. It's free to operate solvent. We open all data. It will be no IPs basically on this solvent. We publish everything so that all partners can test, and any other beyond our project consortia can test it. The solvent was developed in the previous EU project HyperCap, and some data on it already published. Solvent management technologies. Here, IP belongs to TNO. It's oxygen removal technology, in situ oxygen removal and in situ ion removal technologies to maintain solvent and to reduce its degradation. We will do also test with plastics, with different plastics materials on construction, and we will do in collaboration with another project where a mini pilot built completely from plastics only will be used to see if avoiding any metal parts will significantly reduce degradation, and where are the critical parts. So oxygen removal, it's just a small picture here. It's a membrane contactor. Ion removal, we will use sorbent. So this is a good mix of different technologies in our project. Then we will do process integration, and we will study non-linear model predictive control and demonstrate it also that using smart process control, we can reduce operational costs also, that the process will be controlled by models, not by operators. And in our project, this is especially important because we will apply multi-absorber and single desorber concept so that the solvent so the different flue gas sources have their own absorbers close to the source, and then we transport liquid rich with CO2 to a single desorber, which is located where there is space and maybe closer to the source of available energies. As I also already mentioned, open access simulation tool we will offer to test different refineries where this multi-absorber concept will be implemented. And our education and public engagement program was presented yesterday by University College Cork. In addition, we will do evaluation of CCS readiness levels, use the methodology developed by Global CCS Institute on country. We will scale it down to refineries and areas, clusters, to see how if it's what are the barriers and what are the limitations for CCS in those areas. So this is our ATEX. This is mobile pilot that is used at that is built at TNO recently, and it will be built in a container to make it ATEX proof. So it will be slightly pressurized. Its requirements and specifications were discussed with the refineries and approved. So these containers will be moved to our first refinery test site in Cork, Ireland. Here we have issue already because of COVID-19 and travel restrictions. The campaign should have started in January, but now we are waiting until we are allowed to travel. So, and hope it's that after summer we can continue. So this activity is on hold, waiting in our project, unfortunately. And full height pilot plant. It looks like this. It's operated in SINTEF since 2010. You can see we have we have two flue gas sources that we can generate and imitate flue gases from propane burner, and we have a bio or coal burner, so we can, in addition, add those impurities that are critical when we see it from the refinery to the flue gas, and test in this pilot. So we have infinite desox removals, we have pulp filter. We can add aerosols to study and emissions, because I don't know if you have heard, in solvent technologies, aerosol formation is a big issue because it brings some emission spikes during absorption process. So for this will be studied with different simulated flue gas. It depends on what we will go for, which flue gas from refinery we will reproduce. So CO2 liquefaction unit is already designed. It will be connected to this facility in June 2021 this year. So, and it will be a 3-stage compressor unit and cooling in between. Next. So why we focus on degradation? This is an example what can happen. And this is one of the simplest amine systems, MEA in the middle. So a lot of reactions can happen due to impurities in the flue gas, and in particular, oxygen has very high effect on solvent degradation. CO2 presence also in the presence of CO2, and metal parts, iron, can catalyze many of the reactions. But please don't misunderstand, these are not the main reactions happening in the amine plant. These are very minor amounts. This is a really small amounts of solvents that have this by side reactions. Most of the amine reacts with CO2, and CO2 is captured. However, you can probably see in some presentations that with MEA in particular, solvent replacement due to degradation, it's really an issue. Its issue was in the boundary dam with their solvent, and this is an issue with MEA solvent when one of our partners in other projects said that they have to renew the solvent holder almost every month. So this is critical to not have a solvent that degrades quickly. In addition, degradation product can be volatile and be emitted to atmosphere, and they can lead to foaming, corrosion, and other stuff. So that's why we're focusing on this, and we believe our solvent is much more stable. It was tested in the lab scale, and the results were very good. Where is my mouse? Something. So degradation analysis and identification and quantification of degradation compounds and emission compounds, it's really not easy stuff. And fortunately at SINTEF we have advanced chemical analysis lab that was working in this area for, again, from the beginning of 2000, and has developed a lot of analysis methods and have a really nice facilities for analyzing and identifying. So they can identify from this group of peaks every single peak. So it's really, and here is an example just to show how the emissions are measured in real plant. This is an MTU, Aker Carbon Capture's pilot facility, about 25 or 30 meters height, the column, and emissions should be measured on the top of the column to see that there are no hazardous compounds coming out from the amine plant. We have three business cases. One business case will be for Ireland, where CO2 will be captured and planned to go for storage either by ships to Northern Light or maybe by pipeline into the gas depleted reservoir close to the shore here in the island. And then also our models and tools will be tested and evaluated by our partners in Korea and China, where CO2 will be captured and transported to AOR in case of China. But Korean partners, they want to evaluate if this CO2 can be shipped to Northern Lights. So, but I think they have a Japanese project closer, storage project closer. So maybe we suggest them to evaluate that one. I think my time is up, and so it's my presentation. This is our industry club, and it's open for other industries to join. That's all. Thank you.
Thank you very much for your presentation. We are out of time, but I would like to leave a few minutes for a few questions. So please write down your questions on the chat box if you have. I will read one from Harun Magrev. I hope I read your name correctly. I'm sorry if not. So thank you for a great presentation. How do you sample and analyze the carbon dioxide composition? Also, supercritical or liquid carbon dioxide is a strong solvent which could attack some plastic plant components. Any thoughts on this? So you have basically two questions from Harun.
Yes, thank you. I see the question. Well, the sampling and analysis of CO2 is a task for our analytical group. It is possible to do. We have equipment and we have examples from the lab scale facilities where CO2 is sampled and analyzed, or it can be, well, it's different ways. We can also take a depressurized or evaporate, depressurized part of the liquefied CO2, but this is still not this. I think we are deciding how to do this. But this is doable, and when we do it, we can share information about that. So supercritical or liquid CO2 is solvent. So we will definitely not use plastic for intermediate storage tanks. But in the amine absorption plant, there are no parts where we have liquid CO2. So plastic components will be not used there.
Thank you. I have one question of my own. So you said that you are using a new solvent that was developed in a previous project, and this solvent has better thermal energy management and also degrades in a lower amount than normal solvents.
Mm-hmm.
Could you explain a bit why or what is the chemistry in this solvent?
Oh, yes.
It's too much to ask right now.
No, but to just short answers, the solvents, it's a different amines, and depending on what kind of amine you have, there is a different heat of absorption or heat of desorption that you have to apply. MEA is primary amine, and for any other primary amines, heat of absorption is about 85 kilojoule per mole, and this limits what will be the thermodynamically possible lowest heat of solvent regeneration. Our amine, we call it bicarbonate forming amine. Main part of it is tertiary amine, and all tertiary amines have much lower heat of reaction with CO2, so and heat of desorption, but they have other limitations like low kinetics and have to be promoted. So this is the difference in with the MEA, that it's different class of amine, type of amine.
And about toxicity, is this an issue if there is a spill or it's lower toxicity?
Yes, that is a really good question. That's what we test first. We test all our amine candidates when we select them on the biotoxicity and ecotoxicity, and select only those who are not on the red list, like NDA, which is well-known tertiary amine, is a red amine, so we will not use that one. Piperazine is also well-known and widely suggested. It's also a red one, so we are not going for those. There are no green amines because they are not on Plonner list, but yellow, which have acceptable biodegradability and ecotoxicity, that are our amines.
Okay, thank you very much. It was a very nice presentation.
Thank you.
So we go to our next speaker, which is Dr. Kannelopoulos. Could you please share screen, please? I see that I think he's not here.
It doesn't appear online.
It doesn't appear. Maybe it will appear later, so I suggest to go to the next speaker, if you agree. Mr. Paul Godben, could you please, and Professor Abandes, could you please start your presentation?
Yeah, sure. Hello, everyone. I'm Paul Cobden. I'm presenting today, also on behalf of Professor Carlos Abanades, who's not joining, and I'm going to be presenting about the pilot preparation for the C4U project. Let me stop sharing my face and start sharing my screen. Hopefully you can see my presentation now. So this is a part of the C4U project. We have two different technologies that we're demonstrating for CO2 capture and utilization within the iron and steel industry, although we're not doing actually any utilization demonstration. We're just testing these two types of new types of capture technologies. There are 23 partners within C4U, and only 11 of them are taking part in the actual pilots. I think the most important ones are CSIC, where Carlos is from, which is the technology provider for the CASO process, and TNO, which is the technology provider for the displace process. We're using gas in one of the pilots from ArcelorMittal, the world's second largest steel maker. Wood is an EPC who are looking at helping the integration in work package 1. In fact, today there's a HAZOP session on the displace process. So I think if anybody's ever done a HAZOP, they understand why I'm presenting here as opposed to being part of the HAZOP. Ineres from France are looking at CO2 quality, doing a lot of measurements from the different technologies. JM, Johnson Matthey, Kisuma and Carmeus are supplying the materials used within the project. Manchester University and Polytechnico are supporting with modeling. Sverim is the other site where we'll do demonstration. We have one demonstration site in Spain and one in Sweden, and there's also some work being done for the CASO process in Canada. So if you know me and Carlos, then actually C4U is a typical project that goes atypical. Carlos is very much known for calcium looping. This is a 2 megawatt or 1.8 megawatt system in Spain, and I'm pretty much known for sorption enhanced water gas shift, a post-combustion and a pre-combustion capture technologies, one using calcium, one using hydrotalcide. But in fact, we've switched it around in this project, and that's come through an interaction through a project called Ascent, where the parts of the technology we use for pre-combustion are now going to be used for post-combustion, and some of the technology that's used in post-combustion will be used for pre-combustion. So what does that look like? Excuse me. So we have two sites at which we're going to do the industrial demonstration. One is ArcelorMittal in Spain, and the other one is at Sverim, which is right next door to SSAB, the largest steel producer in Scandinavia. There's about 4,000 kilometers between the two. The CASO process, which is the pre-combustion, will be demonstrated in Spain. It's a calcium copper process, and the displace process, which is for post-combustion, will be, which uses hydrotalcite, will be demonstrated in Luleå. Now, today, this afternoon, it's going to be 17 degrees C in Asturias, and this morning it was -24 in Luleå, which means the 4,000 kilometers we have between us, that's around about 1 degree C per 100 kilometers is the temperature gradient. Now, I don't say this for nothing. It's because we also have temperature gradients within our two technologies. Typically within the CASO process, we're talking about almost up to 1 degree C per millimeter. And in a displaced process, it's more like 1 degree C per centimeter. So let's get on to the status of our pilot preparations. Our project began in April of 2020. We both have similar activities, although we're split over 2 work packages. CASO and Displace will both have 2,000 hours of demonstration at high TRL, and most of the activities of last year and this year are all to do with engineering, procurement, and construction. Now, Displace has much of its equipment already in place, and its main task is linking everything together and the new way of working, where CASO requires a new pilot installation and building. The status of both is that they've achieved their respective deliverables on the basis of design, especially paying attention to things like equipment delivery time. All the mass balances, operational velocity of the pilots have been worked out, and all of the responsibilities of the involved parties at the different stages have been worked out. I think this is really important to stress, is that you have a description of action which tells what you're going to do, but when you go to this high TRL level, you really have to think very carefully about what's going to happen exactly when, which partner is going to come in with its materials or its design stages at every single stage. So it requires really quite a lot of extra preparation to make sure that everything goes wrong. Because, you know, when you're running a 2,000-hour demonstration, it can't be something that you're missing halfway through, because you've got potentially 20 people working at a plant at one time, and you can't just have them all go and pause and do something else while you have some problem to solve. And so it really is a different type of research project to many other projects. And I think with the team that we've got assembled, that we're really experienced in doing this kind of work, and so we'll really be successful. Of course, COVID has also put a dampener on things, but until now we haven't really had an effect of that. In the engineering phase, sometimes it's interesting and good to get round a table all together, and that's something we haven't been able to do. But until now, the online tools we have available have been good enough to get through with a minimum of extra effort. Now, so what are the technologies about? Now, I think Vincenzo Spallina showed this yesterday in his presentation of the integration of the C4U technologies. There's 2, there's the CASO and there's the Displace technology. Within this, there are many different sources of CO2 within a steel plant, from the blast furnace, which has the largest amount of CO2, to the oxy steel, to the coke oven. There's also CO2 from a sinter plant or from a pelletizing plant. There's CO2 from the hot stoves. There's CO2 from the reheating ovens. And the way we've pitched C4U is to divide these streams up between the different units, in that all the pre-combustion gases, sorry, including CO, are going through the CASO process, and all the post-combustion gases, so after combustion, are going through the Displace project. So let's move on. So basically, what is the Displace project? I'll get onto a deeper description in a bit, but it's basically trying to use a hydrotile site-like material to absorb CO2 and displace it with steam. And in the CASO process, we're using a calcium, a copper based material, where we have a cycle designed to generate either a fuel gas without CO2 in it, or a CO2 product at high temperature. And I'm going to jump into both of these processes now, first starting with displace. So displace, the technology objectives are to run 2 1,000-hour campaigns. The first campaign is called the nitrogen hydrogen campaign, where we separate hydrogen from blast furnace gas and subsequently use that hydrogen in the chamber furnace. This is a picture of the chamber furnace. In the displace campaign, we'll be doing oxy-combustion of blast furnace gas in a walking beam furnace, and then doing the CO2 capture from this oxy-combusted gas. This is a 3 ton per hour walking beam furnace. If you're wondering what reheating furnaces are for, this is a picture of a real one. This is a 2.4 megatons per year walking beam furnace in Poland from ArcelorMittal. When the slabs have been cast, they're generally left to cool, and when you want to roll them into sheet steel, then you have to reheat the oven, reheat the steel. And so before they go into a rolling mill, they are heated to high temperature such that they can be rolled. Now, typically this isn't a lot of CO2 compared to the whole plant. It's only 3% or so. However, the gas coming out of a walking beam furnace is representative of a combusted gas that also comes from other parts of the process. And so if we can demonstrate for CO2 capture from a walking beam furnace, we can also demonstrate for capture from these other types of streams. Now, of course, here in Luleå, we have already significant pieces of CO2 capture equipment. Here's a water gas shift reactor, which will be used in the nitrogen hydrogen campaign. Here's the 10-meter long column, typically used for CWAX, but now it's going to be used for the displace process. And I've added this one as well. This is a syngas cooler, because this is an important part in thinking about the integration of capture technologies with the rest of the plant. The CO2 coming out of this system is at 400 degrees C. In fact, the CO2 coming out of the Casso system is even higher in temperature, maybe up to 900 degrees C. So it's really important to think about how you can use that heat within other parts of the process. And this also shows immediately what the difference is between a pilot and an actual demonstration. In a pilot, what we're doing is we're just simply cooling this very hot stream down so it becomes manageable. But in a real environment, you'll really want to look at how to use that heat sensibly around the rest of your plant. So what does the displace process look like? We've got oxy-fired BFG in the reheating process, producing a mixture of CO2, nitrogen, oxygen, and steam. That's going into an adsorption bed filled with hydrotalcite material that's been promoted with potassium, and that picks up the CO2. In another stage, we add in steam to regenerate the CO2. Now, the big difference between this process and something you might be more familiar with, which is sorption enhanced water gas shift, is that this occurs at significantly lower pressure. Remember, the blast furnace gas is available at only just over atmospheric pressure, maybe sometimes even only 50 millibar overpressure. And if we think about CWAX, normally we do that at very high pressure, somewhere between 15 and 25 bars. But to avoid having to compress the blast furnace gas too much, and because of some new phenomena that we've noticed on the hydrotalcites, it's actually possible to recycle some of the steam coming off during the adsorption process. There's a displacement process with CO2 and hydrogen, sorry, CO2 and water displacing each other. And so we've designed a cycle where we can recycle part of the steam. So in fact, we only have a smaller, relatively small makeup stream, because we can recycle and reuse some of the CO2. So let's get on to the Casso process. Sorry, I've got something else on my screen. I need to try and get rid of it. Sorry about that. There's just 1 second and I'll be back. My apologies. This is the location of the Casso process. It's obviously, it's still got to be built. This is the gas lab at ArcelorMittal in Asturias. It's connected to all the main gases coming from the plant there. If we look at the Casso reaction itself, it's actually a 3-stage system. First, we put in a fuel, for example, blast furnace gas, which reacts with, well, no, let's start in the Casso process itself. We put in blast furnace gas. Blast furnace gas has got lots of CO2. The CO2 reacts with the calcium oxide in there to produce calcium carbonate. The water gas shift reaction is enhanced. CO2 produced by that is also captured by the calcium oxide, and you produce a hydrogen mixture. Then in a second step, you go to a higher pressure and you feed in air, and the air is used to oxidize the copper that's in there. And this oxidation is very mild, so it doesn't really increase the temperature of the bed, which means that the calcium carbonate doesn't decompose. And then in a third step, you put in the fuel, which can be a blast furnace gas or nitrogen or natural gas. And in that case, because the copper oxide reacts with the fuel to produce CO2 and water, and the copper, and this is an exothermic process, it produces enough heat to do the decomposition of the calcium carbonate into calcium oxide and CO2 again. So this is a 3-step process in which you are producing a hot nitrogen product and a hot CO2 product, and also a hot nitrogen hydrogen product. And there's choices of fuel that you can use during the regeneration step, which will affect the quality of the CO2. Within C4U, the main drivers for the pilot design have been, it has to be a single packed bed. The demonstration of the reaction stages is actually the priority we have to show here. So these different steps within the process. The TRL scale, it's a total of about 1 megawatt. A total that's 0.7 megawatts in heat and 0.3 megawatts in terms of the LHV of hydrogen you will be producing. And an indicative size is around about 5 meters high. And of course, the major thing is to keep within budget. If we look at the designers we have it at the moment, for the plant, I think we can talk about a couple of things. I think one of the additional constraints for our pilot was that we wanted to avoid high temperature valves. These are very expensive and don't necessarily add to the demonstration purposes we have here. And so also to save costs, we're limiting the operating pressure to 10 bars. Remember, the operating pressure is about the production of or the step where we oxidize the copper. So we get it ready for its reforming reaction. And typically, if the higher that you choose in the pressure that you do to do that, the less CO2 you lose within that step. Now, other considerations, we went into a thing called a common design practice. And that's so we've got a detailed process description now, all the reaction and heat removal stages, the mass and heat balances of all the CASO pilot operation modes. And most importantly, as I said before, we know very well what every participant in CASO is going to do to achieve the parts of the relevant parts of the project. Now, I just want to show this. I don't want to go through it, but in one of the considerations within the within such a pilot, it's very different to a lab operation. You really have to think a lot about how am I going to start this whole thing up. And so there's been a whole design session based on what are all the steps. How do I get from the position of having a cold reactor to a reactor at that's potentially going up to 900 degrees C? And so there's a lot of considerations going on here. There's also needs to have the consideration, what happens if I have an emergency shutdown during my regeneration step? How do I get back to my full operation? What happens if I have an emergency step shut down in a heat removal step? And so all these considerations are put together when designing such a pilot, and these are very different to a typical operation of a lab scale reactor. Now, one more thing about the reactor. Here's a diagram of it. You can see that we're using water cooling coming out of the hot gas coming out of the packed bed reactors, and that sample materials from Carmeus, that is a large lime supplier, and Johnson Matthey, which are supplying the catalyst, have already been delivered. Now, in the same way that CASO is working this out, of course, for Displace, we're also looking at these kind of things, but in the because of the time, I'm going to skip through this. I think confidential was left down there by accident. This is not confidential, but this just shows what we're looking at within the pilot. We've got more than 400 meters of pipeline that needs to be installed in order to connect the different parts of the units together. So I just want to finish up again with the status of the pilot preparations. Okay, we have similar activities in both the work packages that represent both CASO and Displace. 2,000 hours demonstration at high TRL. As you know, we're still in the engineering, procurement, construction phase. And we've finished the deliverables on the basis of design and also on a common design practice, because we've got lots of partners coming together with this project. We have to make sure that everybody's aligned, and it's a very exciting project, and we're really happy to take it forward. Now, one final sheet I have is on the synergies between the CASO and the Displace process. Of course, I started talking about the fact that generally in the beginning, I was very much into pre-combustion, and Carlos very much into post-combustion. This is a way that we can work together. The CASO process will be looking at, coke oven gas, basic oxygen furnace gas, blast furnace gas, and also nitrogen hydrogen product as a fuel. The actual demonstration will only be on blast furnace gas. Displace process could be used in the sinter plant, the hot stoves, the reheating furnaces, and also for the case that we use blast furnace gas in the CASO process as the regeneration gas, then there'll be nitrogen from the blast furnace gas in that CO2. And so Displace could be used with the proper heat integration as a way to improve or decrease the amount of nitrogen in that CO2. At the same time, the nitrogen hydrogen product that is produced by CASO could be used in the reheating furnaces and the hot stoves. And in that way, Displace is actually proving some of the use of the CASO in the other units. So there's lots of integration possibilities between the two different types of technology. And that's where I'd like to leave it for now. Thanks for your time and thanks for listening.
Thank you very much for your presentation. We are a bit behind schedule, but I think we should at least address one question if you are willing to share with us on the chat. In the meantime, I would like to ask, maybe I'm not very familiar with all these technologies, so if I'm wrong, please excuse me. So I saw that you are mentioning also hydrogen-nitrogen separation.
No, in fact,
somewhere in the processes.
One of the issues with blast furnace gas is it contains an enormous amount of nitrogen. So typically 50% nitrogen. The great integration that you can do within a steel plant is that you need all these reheating purposes, so you don't necessarily have to remove the nitrogen before you use that gas for a reheating purpose. And that's one of the classic improvements that can be shown by using that nitrogen hydrogen mix. If you want to use the hydrogen for other purposes, such as for reaction with CO2, then you'll have to clean up that hydrogen. And there's different ways of doing that. Within the Casso process, you can look at using a different fuel during the hydrogen production stage. In the other process, it's possible to use membrane systems for separation of nitrogen and hydrogen. And in fact, that was done in a pilot campaign just before Christmas, where at Spherium we produced methanol from blast furnace gas. We produced around about 30 tons of methanol from blast furnace gas, and that's going to be used in a ferry that goes from Kiel to Gothenburg. There's one ferry that runs on methanol now, and we've now produced steel-based methanol for that system. And in that project, we had to use a nitrogen-hydrogen separation because there's too much nitrogen in blast furnace gas. Even if you remove all the carbon, there's still too much hydrogen.
Okay, I'm very happy to hear my favorite word, membranes. And yeah, because hydrogen-nitrogen separation with membranes is relatively easy. So thank you very much. I see there are no questions on the chat. I would like to go to the next presenter or to the past presenter, but I see neither of them are logged in as far as I looked just a moment before. I'm looking again now. So I would like to go to the last presenter, and then maybe I will try to fetch if maybe the two ones that are missing are in a different session by mistake. So I will, Alessandro, if you could go and search for them, maybe they are there. So please, I invite Dr. Roses to give the presentation.
Hello, good afternoon. I guess I have about 45 minutes for the presentation, so I'll take my time.
No, please stick to your time. No, and hopefully we will find the other two presenters somewhere.
Yeah. Let's see if you now see my screen in full screen mode.
Yes, we can see it.
Okay. Yeah, so the title of my presentation is Design and Development of a Membrane-Based Post-Combustion CO2 Capture System. So your favorite word on membrane. The outline, yeah, first I'd like to give an introduction to our company, High Gear, mention some comments on CO2 emissions and capture, and go straight to the member design. So, a bit on High Gear, we're an SME, a small company, about 80, now we're about 85 employees, about 20 years old. And we operate in gas supply worldwide, mainly addressing these sectors, glass manufacturing, metal sintering, food sector, and electronics. Our products are, well, what we sell is gas, so our product are molecules, actually. using our own developed technology. So we sell hydrogen, but also sell purified gas or gas by recycling from say used processes, as in the example of the glass sector, purifying nitrogen mixtures. This is a bit on our strategy. We have hydrogen generation systems, recovery systems, and then we look in if we associate this with the TRL concepts we're used to mention, say for a longer time scale, we look at different technologies. This picture is just to show you the interest of our technologies is usually under 1,000 normal cubes per hour. This to give you an idea of why we step into this kind of project, like in the project member, and try to customize solutions for small scale that can be applied to small scale gas production, even with CO2 separation. Regardless of that, in this project, we do the analysis for large scale plants, but in our company, we're interested in small scale on-site production, potentially with CO2 separation. Yeah, this slide is most commercial. I can skip this. This slide shows you our system for hydrogen production. So it's basically known to all of you. It's just a hydrogen steam methane reformer system in a 20-foot container with DPSA for purification. And all the components. Packed in, we have also a system for in a 40-foot container, but that's for 450 normal cubes per hour. So this, the models we have commercial, but you can see this in our website, so I won't stop here. The typical layout of how we assemble the system. For example, these are configuration with two hydrogen 50s. These produce 50 normal cubes per hour with compression and storage delivered to the customer. And design of how this layout can be assembled. And some examples of customer systems as well. Let's move forward to go to the member case situation. We also supply hydrogen for filling stations. In summary about the introduction to our company, we're an industrial gas supplier in small bulk with the ability to design, install, and operate the supply. We can provide the hydrogen as with HAS contracts, which is gas as a service, where we install the system and we operate it, and the customer just has the gas supply fully operated from us. This is a difference between the buy option and the gas, the HAS option. And all this introduction to lead you to the R&D projects. What I'll discuss now is about the member project. Is a project for use which uses membranes for CO2 separation in pre-combustion and post-combustion. Particularly now, I'll talk about the post-combustion one. And these slides showed you that we've been approaching, say, technologies using membranes in the last years because this gives a lot of flexibility for designing small-scale units for on-site purification and gas production in the scale that we're interested in. These are some examples of past R&D projects. Moving on to member. Well, the problem of CO2 you are most aware of. The project looks at the CO2 emissions, particularly in the power production sector, as I mentioned, for small scale, there are other sectors that are of interest and should not be neglected just because they have a lower share of CO2 emission. Depending on the well, there's quite some potential for CO2, both utilization and storage. This was discussed in the previous presentations by other colleagues. But depending on the application, the requirements of purity are strongly affected. Can be as low as 90% from some applications for enhanced soil recovery, and as high as food grade. And this only shows the CO2 content, but of course the requirements for the impurities those vary strongly, and that opens or closes the possibility of using certain technology like membranes. In our case, we are looking at a design that can target the 95% purity, which are suitable for the membrane technology that we're using. It's debatable whether it would be economically for other applications or for other users, for example, for food sector, but that's more for the membrane experts. So we're looking at the post-combustion in this presentation, even though within the project member, we develop technologies for pre-combustion and post-combustion CO2 separation. On post-combustion, well, at large scale, the technology is quite so the benchmark technology is quite well known, using chemical absorption-based system. Physical technologies could be suitable and are proposed for smaller scales, and when also in situations when CO2 partial pressure is lower. Yeah, compression is needed in those cases. If you want to have a look at the detailed description of the benchmark technologies and the requirements that we used in the project member, there's deliverable D2.2, which is public and it's available on the website of member. You can have a look. The references in the document. For the CO2 separation here, we use perm-selective membranes, which use where the driving force for the emission of CO2 is partial pressure. So that's why, as I mentioned, compression is needed, or vacuum on the other side. In this particular system, we use both. These membranes have a high packing density, which help design as a compact system. And for this application, the partners developing the membranes use PEVAX polymer-based composite hollow fibers prepared by deep coating of porous hollow fiber supports, and MOFs will be in the outside coating selective layer. I'm not a membrane expert, so for details of the membranes, you can contact our partners in the project. The goal of, well, at least the aim of the project is to reach TRL 6. So there are partners, there are industries in the partnership in order to validate the pilot setup with real gas coming from industrial sites. For the post-combustion, this will be in Portugal. Within the project, I mentioned already that we will demonstrate pre-combustion, post-combustion separation, and also hydrogen production with CO2 separation. in the particular case of post-combustion, this is the reference carbon capture ratio and the reference cost of carbon capture. And we aim to get these numbers. The prototype for post-combustion in the project is called Prototype B, and the facilities where it will be tested, the demonstration scale is Gallup. This is in Portugal, aiming for this 90% carbon recovery and this reduced cost. It's a picture of the site of Gallup. It's not the best picture actually, but yeah, at the site they have two sets of natural gas fueled power generators providing about 9 megawatt of power. On the specifics of the membrane that will be used, so the target of the project is to have a membrane that can have a permeance of 300 in GPU, selectivity CO2 nitrogen of 70, membrane area up to 10 square meters, that is per module. Actually, we'll have two modules here, but of different areas. Design pressure of 7 bar and membrane cost, final cost of under 100 euro per square meter. And these are the targets of recovery of the whole overall system and on the purity. I should say that originally in the project we had set 90% of purity, but later we decided to have a external scope 95, given some discussion, and the design of the system is done for this 95% of purity. The pilot that will be demonstrated has a feed flow of 10 cube per hour with atmospheric supply pressure, so we'll have to compress within the system. And the gas composition has about is quite low in CO2, so about 6%. And these are the selectivities, at least at the modeling phase for CO2 water, CO2 oxygen, CO2 nitrogen. This is the most important one. And we looked during modeling at 1 or 2 stage layouts. Yeah, 1 stage layout is the one showed here in the top. Is quite simple. We found out quickly that we could not reach the purity targets, so we discarded the 1 stage layout. We moved for 2 stage layout with recirculation after the second one. Basically, we have compression of first stage, then we have vacuum, compression, and the second stage with this recirculation here. These are the results on the separation in both modules, and yeah, mentioned here we have a vacuum pump and the permit of the first stage. We did some results on sensitivity to the parameter or to the performance of the membrane. In particular, if we look at the sensitivity to permeance, for example, lower permeance will affect the recovery in this configuration quite strongly. This can be balanced or countermeasure could be play a bit with the pressure. So by increasing the pressure, we can stay within the goals. Of course, at a higher OPEX, that would be the downside. We looked at the sensitivity to the selectivity of the membrane. If the selectivity is not good enough, we might not be able to reach the purity. So both permeance and selectivity are important, but each having a different effect on the final outcome. Well, in conclusion, the prototype for post-combustion CO2 capture, will be demonstrated at an industrial site. This is now the phase of construction at our facilities in Netherlands. We will do an FAT at our site. This will be around summer, and then the second half of the year send it to Portugal for the long-term testing. It's expected that it would run about 6 months at the site. The prototype design with 2 stages it's expected to meet the target of 95% security and recovery above 90. We have 2 stages where the first one is actually of 10 square meters. The second one is much smaller, maximum operating pressure of 7 bar. And regarding the performance of the membrane, the selectivity is very important to reach the purity. And there's not much we can do to compensate for that if the selectivity of the membrane is not that good. We can compensate for lower permeance if this happens by adapting the operating pressure. And yeah, this system will be installed in a 10-foot container, so a closed housing, and installed outdoors. And I think that's all I have to say. Hopefully, when the system is running, then in the next conference I can show some test data. Thank you.
Thank you very much for your presentation. If there are any questions, please write them down on the chat. In the meantime, I have one question. I would like to understand a bit more about the compression costs. You were saying that the maximum you would use is 7 bar. What happens with the cost afterwards in relation to the pressure and also with the flow rate that you would use in a real application?
Well, in the setup, I mean the compressors that we have already selected were for that pressure, let's say, because from the system modeling that appeared to be sufficient. But say there's no limitation if in the future the performance of the membranes indicate that the setup would need a different pressure. One can go for a system with higher pressure. I mean, from system design point of view, one can go as high as one wants. But one would need to look at the technical economical analysis to see if that still pays off and can guarantee the 40 euro per ton of CO2.
Okay, thank you very much. So now we will go to the. We have one question. One more is well, 2 of them.
I see the pressure. Yeah, 7 bar would be the pressure that we compress to for the first stage. What purity of CO2 you reach after 2 stages? Yeah, the 95% purity. What will be the permeate CO2 pressure? Well, we have in the modeling we derived that with 200, or sorry, I think it was between 200 and 300 millibar absolute would be sufficient. But just to be on the safe side, we bought a pump that can go much lower than that. So we can go down to 60 millibar output. But I don't think we'll need to go that low. Would you say something about what would happen to impurity if they were also present? Yeah, well, in this case, we didn't look that much into the H2S issue because at the site where we're getting the gas is already exempt of H2S. But yeah, of course, if another emitter would have gas with impurities, we'll have to design it ad hoc. But in this case, it was not an issue. I expect the issue would be with the membranes, but I'm not a membrane expert.
Yeah, so it can be an issue. So sometimes people do aging tests for with H2S with membranes. But for the next question, from the membrane point of view, carbon monoxide is not an issue. I don't know if for something else can be an issue.
for the other, let's say, equipment in the system is not.
Yeah.
Sure, no.
We have two presentation that still are should be due to present, but neither of the presenters are here in the participants. So, okay, for those of you that are still here, I would like to close now this session because in the 3 minutes that are left, nobody will be able to present, even if they manage to get in. So please remember that after lunch, there will be a round table of discussions. Let me see at which hour. At 2:30. So please remember to attend to this if you have time. Thank you very much, and I wish you a very nice day.